regard to fluids, we talked about fluids that are not moving. They're static fluids. We had some important big ideas that the pressure deeper in a fluid is equal to the pressure higher up plus the column of water above. That was one big idea, yes. Very important. And then we also talked about the idea of buoyant force, which is Archimedes' principle, where we said I take the density of the displaced fluid times the volume of that is in the fluid. If it's the entire object, it's the total volume of the object. If it's part of the object, it's whatever fraction of that object in the water or fluid. Rho v what?
GH.
Mass times m times g. Buoyant force is really m times g. If you think about it, it's rho times volume gives me mass times g. But we have to be careful with these subscripts. This is the thing that will trip you up, I guarantee it. Remember, buoyant force is the weight of the fluid that has been pushed aside by the volume that is in it. I'm going to say it again. The buoyant force is the weight, mg, of the fluid that has been pushed aside by the object that is in the fluid. Okay. People get this mixed up all the time. Please don't do that. So those are the two big ideas we came up with, super big ideas, with static fluids. Now we're going to talk about fluids that flow. And we're going to make our lives simple by imagining this ideal fluid, which flows in a very streamlined fashion. There's no turbulence. It is non-viscous, meaning there's no friction in the fluid. And so it's an ideal fluid, but that makes our analysis so much easier. I just read a quote that fluid dynamics, actual real hard fluid dynamics, is harder than quantum physics. And I actually believe that in terms of the mathematical analysis. So we're going to keep our lives easy, okay? But we do need to talk about, hey, what goes into this ideal fluid that flows? A lazy river, right? It's a nice lazy river, no turbulence, it's just all well behaved. So steady flow, the velocity of the fluid particles at any point is constant as time passes. So if I sit here and I stare at every molecule that goes by that particular point, every time I look at it, it's going the exact same velocity. This one's going 3 meters per second, the next one 3 meters per second, the next one 3 meters per second. It's not speeding up and slowing down as I look at that particular point in the fluid. That's what's called steady flow. Unsteady flow is when the velocity of the particles is changing. So you can imagine in your garden hose, if you turn the water on and you were to sit inside the hose, make a miniature of yourself, and you just watch molecules go by, there's no real reason why their velocity should change, right? Seems reasonable. Now, in my house, I have a pump. So I get high water pressure and it pushes water, and then at some point the pump has to cycle and add more pressure to the system. And when that happens, I might get different velocities. That would be unsteady flow. But for most of you who have city water, if you turn the tap on, you watch the molecules go by, they're well behaved. Seem reasonable? Yes.
So like a power washer would be an example of an unsteady flow?
In what sense? This groovy flow here, very groovy flow. No turbulent flow for us. No swirling water or white caps. If you've ever been white watering, you know what I'm talking about. We've got ourselves a lazy river, okay? It's well behaved. Fluid flow can be compressible or incompressible. Note that most fluids are nearly incompressible. So if I took a block of water and I apply pressure on all 6 sides of that block of water. The idea of being incompressible means I cannot shrink its volume. Okay? It's not actually the case, but it's pretty darn close to the case. Okay? Most fluids are nearly incompressible. Air, however, is compressible. As you know, you've heard the term compressed air. Or liquid nitrogen, right? Liquid nitrogen. Nitrogen is a gas. It can be compressed and down to a liquid. Viscous versus non-viscous. Your pancake syrup is considered viscous. Doesn't flow very easily. Pancake syrup, what else is viscous flow?
Honey.
What's that? Honey. What's that? Molasses, super slow, right? That's viscous flow. Doesn't flow very easily. Yes?
Does that mean water is non-viscous?
It not truly non-viscous, but it's close to being non-viscous. Doesn't have a lot of frictional flow, if you will. Okay?
Doesn't its viscosity change as you like heat it up?
You're talking about the density.
Oh, okay.
The answer is yes. Densities of fluids can change from one point to another, but for our purposes, we're going to assume the density is the same everywhere in the liquid. Okay. Why do we do this? Because it gets super hard if you don't do this. If you don't do this, we don't have the math to do it. And it's not just Calc 1 or Calc 2 or Calc 3. It's advanced Calc 3. So I'm telling you, it's super hard math. Okay? We need to know about curl and divergence and all kinds of other crazy stuff. So we're going to work with these things. Like, yay, go team! Incompressible, non-viscous fluids. You like it? Perfect. Done. Streamlines. All right. We do need to talk about mass flow rate because it is something. So what does a rate sound like?
A rate?
I mean, what does it, when you hear rate, what does it evoke in your mind?
A change of something over time,
Something per unit time. So what does mass flow rate sound like?
mass over time.
Mass over time. Seems quite reasonable. So our assumption in all of our flowing water is that there are no leaks in the pipe from source to exit, okay? There are no leaks, so that means the mass flow rate throughout the pipe is more or less the same everywhere. If we had leaks, of course, in front of the leak I'd have one mass flow rate. After the leak I'd have another mass flow rate, which would be different. So we have to assume we don't have any leaks or additions necessarily to our system. Oops, sorry. So let's talk about that. Looking at this groovy picture, here I have liquid, fluid in a pipe, flowing that way from left to right. Delta M is the amount of mass. So if I take rho, which is density, times volume, that gives me mass. Rho times volume gives me mass. If I take a cross-sectional area for my pipe here, realize that this cross-sectional area is bigger than this cross-sectional area. You can see that, right? If I take cross-sectional area times this length, what's the volume of a cylinder? You guys remember? Anyone? Anyone? The volume of a cylinder is area of the base times the height, or pi r squared h, or if I draw a picture, that's not a good cylinder, but that's a, or pi r squared, and that is h. That's the volume, yes? It's like 1/4 is a slice, and then I add a bunch of quarters. I've just built a cylinder out of slices of volume, right? So what they're doing here is they're assuming we have a pipe with fluid flowing in it, they're building a volume element. They're saying I'm going to take the cross-sectional area times this height of my cylinder. Well, if I take the speed at which the fluid is moving times time, meters per second times seconds gives me meters per second times seconds gives me meters, yes? So area times height. This is actually the volume of that guy over a period of time in which the fluid flows some distance. Okay. And likewise, if I take this area times this height, that's the volume of that cylinder. You guys tracking? You don't have to be able to do all this math. I'm just trying to build the ideas in your mind. So in some period of time, delta t, I get this disk of fluid moving, or this volume or mass developed in this fashion. And I can now divide by time over here, and it leaves me with rho times A times V. You guys tracking? So let me write that out. So at the front end of my fluid, I have the amount of mass in that big thing over delta T is rho times area 2 times volume at that point 2. Or is that 1? It's 2. Are you guys tracking on this? Please tell me yes. Okay. And at the far end, I've got this going on. I've got rho times A1 times V1. Now here's the big idea. If I have a hose, even if it skinnies down like this, the mass flow rate, the amount of mass per unit time has to be constant if I have no leaks and no additions to the system. So there's no pinholes here where water's coming out, because that would imply the mass flow rate here is bigger than the mass flow rate over here because it had leaks in the system. We assume no leaks, so the mass flow rate has to be the same in the entire pipe. How much mass of water is flowing per unit time? And if that's the case, what can I do with these two things? What did I just say in words?
That they're equal to each other?
That they're equal to each other. That's essentially what I just said. So if the mass flow rate has to be the same in the pipe, I can set this equal to this. Or this equal to this. Anybody see something interesting? If we assume what is true, what can I do to this equation? Say it, May.
That it's conserved.
Well, it is conserved. We've kind of said the mass flow rate's the same. But what about now looking at this? Any ideas? If the density is the same everywhere in the pipe, density of the fluid, I can cancel these, right? There's incompressible, I assume the density is the same everywhere. So I end up with this actually very important result, which is called the equation of continuity. Are you going to send that to, there's you? Wash your hands before you eat. She has norovirus, or her kids do.
Oh.
You don't have to write down all the words, I've already said these, but realize for a single entry and a single exit from the fluid flow, this is true. Mass flow rate has to be the same. And if I assume these two densities are identical, which we will, then they cancel, and I get this important result at the top for incompressible fluid. Okay. So let's look at this. We're gonna go backwards to another picture we had before. That guy. I want somebody to look at this picture and this equation and make a wise statement.
Decreased area means increased velocity.
Decreased area means increased velocity. So let's think about the garden hose. This is a garden hose, and this is a garden hose where you put your finger over part of it, as in this illustration. Are you or are you not constricting the area from larger to smaller? Okay, let's call this A1 and call this A2. So velocity 2, the velocity of the liquid here at this point is equal to A1 over A2 times V1. I just manipulated this equation. Okay. So you'll see this velocity at the end of the garden hose is bigger because A1 is bigger than A2. So that ratio is more than 1. If I multiply by the velocity of the liquid going through the hose at that point, then I get a higher velocity coming out the end of the hose. How many people have done this? Put your finger on the end of the hose. Why do you do it? So it comes out faster. Yes? Instead of, that's not useful. It's not useful, right? It's boring. Psh, spray your friends, right? Yeah, that's right. All right, questions about this continuity equation? Anyone? 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 Why is it called the equation of continuity? Why?
Because it remains the same.
What remains the same?
Very basis.
The very basis which I said was what remains the same in the entire pipe?
The density of the fluid or
Yeah, the mass flow rate. Good. Yes, that's the important idea. That's how we come up with this. Shall we practice? What the heck?